Good morning, ladies and gentlemen. I hope you can hear me. First of all, I will thank for the kind invitation to this conference. It was a little bit difficult yesterday to arrive here due to technical problems of my airplane, but I finally at 10:30 I made it to the hotel at night. So in the following 30 minutes, I will deal with a difficult topic. I'm a neurobiologist, as I heard, and my wife, Professor Ursula Dick, and I were studying for more than 20 years, among other things, the question, what makes an intelligent brain intelligent? And very briefly, I will give a very short overview, of course, 30 minutes. So first, it was just mentioned, we have to identify or define levels of high intelligence, which include the following abilities. This could be discussed and disputed, but this is a summary of recent literature. Many animals, especially primates and a number of other animals and of birds, can adopt the perspective of conspecifics, for example, in the context of deception and counter-deception. And this is found in primates, but also it's more abundant. To anticipate future events, for example, in the context of tool fabrication for future use. This is found predominantly in apes, but also in corvid birds, as can be read in literature. To understand underlying mechanisms of processes, for example, at fabrication and use of tools. This is clearly present in apes, while data from birds are equivocal, but maybe there are new findings. Self-recognition in a mirror, I will show just a brief example, which has been demonstrated unequivocally and systematically in the great apes, chimpanzees, gorillas, and orangutans, and has been found occasionally in dolphins, elephants, corvid birds. They may be able to recognize themselves in the mirror, but they may not like to watch their own image. But so it happens, but it's not systematically. Knowledge attribution in theory. Oh, I see this is anyway. Knowledge attribution and theory of mind, which is found, albeit in preliminary form, only in the great apes, as far as we know. Maybe corvid birds have it, but it's been not shown. Metacognition, this is the knowledge about one's own knowledge. This seems to exist in dolphins, monkeys, at least in macaques, which we have in our institute, and apes, of course, and humans. And finally, consciousness. And presumably, I believe, many, if not most, vertebrates, and maybe invertebrates too, octopus, have some forms of consciousness, for example, in the form of focused attention, while higher forms of mental act, like self-awareness and reasoning, may be restricted to some birds and mammals, or even only to apes. This is unknown, but I will show an example. So this is a nice picture from a work from Elisabetta Wieselberghi, a capuchin monkey. These little animals can use tools, for example, a stick, to push a peanut into a box. And they are very effective on this, but if Elisabetta turns the box upside down, this little creature doesn't understand that it's helpless to push this peanut upwards into the box. So they don't understand the mechanism. Maybe after 2 years they will learn it. But the great apes not only use tools, but they fabricate them. For example, chimps and orangutans in different forms, for different shapes and so on, and little children observe their mothers. So this clearly reasoning, which kind of tool will I use within the next half hour when I go into the savannah. Chimpanzee in front of a mirror. This is clearly seen in the great apes, maybe in corvid birds. My friend Ono Guntöken has demonstrated in a corvid bird. But this occurs in humans at the age of 18 months. And it's not, and systematically, I just tested this with my grandchildren who are 3 years old and live in Oslo, so they should be smart. But in animals, it happens or does not happen and probably depends on training by society, most probably. And finally, consciousness. This is a young colleague of mine, Julia, 50 years ago, and she was remarkably intelligent in the laboratory of my Professor Rentsch, and she mastered very complicated mazes. So clear, and they did draw a piece of metal after having watched carefully possible ways through the maze. So clearly they have consciousness and they can think how to move to come out of the maze. So the question for a neurobiologist is, can we correlate these kinds of high intelligence and many, many other parts of intelligence in the animal kingdom, even insects and other invertebrates, with some properties of the brain? So what has been discussed mostly is absolute brain size. Then some people were skeptical. Oh, it should more be brain size relative to body size. But then if it doesn't function, it could be that we correct relative brain size for body size, which has been done by many authors. It could be absolute or relative cortex size, because the cortex, at least in mammals or on the pallium in many vertebrates, is believed to be the seat of intelligence, which is, by the way, correct. It could be the absolute or relative cortex size, but as we will see, it doesn't really fit. So it could be something much more special, the number of cortical neurons, which is like a computer approach, or even more information processing capacity. A physical information processing approach to the brain. And in addition, it could be something completely different, seemingly different, the possession of syntactical language. So these are the possibilities. Let's go quickly through them. So in mammals, and I restrict myself mostly to mammals, there are huge differences in brain size from a small size armadillo, but the smallest is in very, very tiny shrew, to hare, dog, ape, man, and then this is a moderately large whale or dolphin brain. They can be really huge, up to 10 kilograms. So we cannot even draw it here. So we see, even if we believe that man is the most intelligent creature on Earth, elephants, as we see, and whales have both much bigger brains and much bigger cortices. So in the next slide we see the problem. The mouse has a small brain, rat, larger brain, cat, 25 gram, dog, 64, rhesus monkey, 90 gram, lion, 260, but rhesus monkey is much more intelligent than the average lion, as far as we know. Chimpanzee has 400, cow 490. Cow has much bigger brain and horse than chimpanzee. How could it be? The chimpanzee is very intelligent. Then gorilla, thank God, has 520, and man, 1 kilogram and 350 grams, but then the elephant has 4 kilo to 6 kilo, and a sperm whale has 8.5 kilogram, up to 10 kilogram, and a false killer whale. So it doesn't really fit. Rhesus monkey doesn't fit, chimpanzee, gorilla doesn't fit, and man doesn't fit. It is not on the top. So there is some raw correlation in mammals as well in other vertebrates, but data are mostly missing. But it doesn't fit with intelligence, not really. Brain size seems to have some meaning for intelligence, but it's unknown how. So the next diagram is a little bit complicated. It's here on the axis, it is body weight, and this is brain weight. And we see if in a double logarithmic scale, the relationship becomes linear. This is simple mathematics. And you see when animals, here mammals, become bigger, 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 and much bigger, up to 1 million kilogram, there's this very, very nice linear correlation, double logarithmic presentation. So when you get bigger, you get a bigger brain. This accounts for more than 80% of brain weight. You could just get big. But there are huge differences. Some, and this is important, some mammals drop below the average. This is the average. For example, hippopotamus, blue whale, shrew, bat, and so on. And in double logarithmic representation, these differences are huge. It's one order of magnitude sometimes. And some are above average. For example, man, dusky dolphin, and the chimpanzee, largely above. So there are differences, although there's an average. Some animals, some mammals have much smaller brains than you would expect, where others have much larger brains. And the question is why? At the same time, when brain size increases with body size, necessarily the relative brain weight, the percentage of body weight goes down, which means when you're very small, you have a high percentage of brain in your body, like in some mouse and shrew, and it goes down in huge animals like the blue whale. Here we have 10% of body mass, of brain mass of body weight, goes down to 0.005 in the blue whale, which is maybe 6-7 kilogram, but the blue whale is enormously large, so it's just a little thing. Whereas in a small insect, insectivore, the brain relatively might be enormously large. So if relative brain weight would count, the insectivores or the shrews and mouse should be the most intelligent, which is not the case. But also the blue whale is not highly intelligent. There are other whales, dolphins, who are much more intelligent. So there again is a problem, and a colleague of mine, Harry Jerrison, for many years already said we have to weigh the enormous differences in body size versus brain size. And he developed what's been called by him encephalization quotient, which just means, written here, defines how much the brain volume, body volume ratio of a given group of mammals, for example man, deviates from average. And the average, for example, is a cat. And the horse, for example, falls below the cat, sheep, mouse, rats. They have smaller brains compared to average mammals. And the cat is just average. Squirrel and dog and camel have, walrus and elephant have slightly larger brains than expected just by increasing body size. This is very important. Then we come to the rhesus monkey, who has twice as large brain with respect to average mammals. So this is astonishing, but not very much. Chimpanzee has 2.5 with a very disappointing capuchin monkey. This is, the age is missing. Almost 5%. And this explains why capuchin monkeys are highly intelligent despite having a very small brain. This is astonishing. Dolphin has 5 times larger brain, but capuchin monkey appears to be more intelligent, after many authors, than a capuchin monkey, and man has almost 8 times larger brain than you would expect from evolution of body size, brain size relationship. So this is very astonishing, and we could explain this in humans. Studying the recent evolution of the human species, it's strong, the brain size relative to body size or body weight strongly goes up, and the maximum is found, as you may know, in the Neanderthal, not in Homo sapiens, but nobody knows what the Neanderthal people did with these larger brains. This is unknown. But we have an astonishing large brain. Within 2 million years, 3 million years, we got this enormously large organ. And it's not known why, maybe just an unspecific genetic effect. There's no environmental effect that correlates with this history. Anyway, so as so far we don't really find a very, very good correlationship. So people say neither absolute size of the brain, nor relative size corrected for body size explains rigidly high intelligence in these animals. So people say, oh no, it's not the brain mass that counts, could be the brainstem and limbic system. It's much more important in lower animals and stupid animals. We have a high cortex. And it's true that a hedgehog has a small cortex, prosimian has a larger cortex, we have a very large cortex, we think. So this nicely explains why man is so intelligent. However, this is not true. First of all, the size of the cortex strictly follows an increase in brain weight. The larger your brain, the larger your cortex. Has nothing to do with intelligence. And you see there's a very strict line, and the proportion and the percentage just increases. And a friend of mine, Rudolf Nieuwenhuis, who drew this, he's a Calvinist. And as a Calvinist, he declared me, he has to stop in his illustration. He is a very famous neurobiologist with man. It's forbidden to think about other animals having larger brains, although he knew it. He could not publish it as a Calvinist, which is interesting. So this diagram stops with man, but this is a much larger brain, elephant brain, 5 kilogram. You see this enormously large cerebellum. This explains why elephants can fly and swim and climb, because traditionally you explain the size of cerebellum by this ability, which is nonsense. They just get big if the brain gets big, the cerebellum, if you use it or not. But they have a huge brain and a huge cortex because they have a huge brain. At the same time, the elephants are not very intelligent. I went to India and studied them to some degree, and most authors, not all, say they are relatively modestly intelligent, but not very much. Even my Professor Wrench studied them for years and say, it's awful to teach them something. Anyway. But there must be something. Why isn't this huge cortex the producer of high intelligence? We go into some details and ask, this is a wonderful cortical surface, but how thick is it? Because surface and thickness determines the number of neurons. And if we study the thickness, it is thickest in the primates and in humans. Here, has a thicker cortex, 4 millimeters, 3 millimeters, 5 millimeters, and the whales and elephants have a very thin or relatively thin cortex, 1 millimeter. And this is astonishing. Here in the next you see, this is a normal cortex. 2-3 millimeters, maximum is 5 millimeters. The cortex, well, this is relatively thick. Often it is, here is 1 millimeter. So they have a huge cortical surface, the dolphins and whales and the elephants, but it's very thin. However, and we have the thickest of all mammals. But in addition, this cannot explain everything. You see something very important. If you compare neuron size to, in humans, cortex of whales, you see, and I just can tell you, whales, dolphins, and elephants have much thicker neurons for many reasons. And they are, in humans, they are densely packed as in all primates, and very loosely, rather loosely packed in dolphins, whales, and elephant. So we find the cortex of these creatures very thin. They have large neurons and loosely packed. And in addition, okay, now knowing this, we can calculate, and my wife and I did this, and other colleagues did this too. We can calculate the number of neurons in the cortex of mammals. Mouse has, this is millions, 4 millions, the rat 50 millions, goes up, opossum 27 millions, dog 160 million, cat has many more neurons, maybe cats are much smarter than dogs. Maybe rhesus monkey, almost 500 million neurons, which is highly unexpected because they're really small and very densely packed, despite a small, very small brain. Dolphin has maybe 6 billion neurons. Chimpanzee has slightly more, but this does not explain in toto the superior intelligence of chimpanzees. Whales, this should be 6,000, excuse me. No, 3,000 to 10,000. This is huge variation among authors. Maybe 10,000, which is enormously high, but not given the large brain. Elephant may have 6,000 or 11,000. Herculano Hausel found 6,000. We found 11,000. Anyway, humans have between 14 billion and 20 billion. Yeah? And so there is some difference, and we are on top again. But being serious, this does not explain the superior intelligence of humans and of primates. And in addition, we have to explain why animals with much larger brains are less intelligent than a rhesus monkey, a chimpanzee, or humans. One thing is they have much smaller neurons, much more densely packed, which means the distance between the neurons, which is very important, is much smaller in primates and very large in elephants, dolphins, and whales. Very important. But in addition, if we measure the axonal conduction velocity from one neuron to the other, first, there's much shorter distance, and secondly, it's 5 times faster in mammals because of a very, very thick myelin sheath, which determines the processing velocity. So, apes, including man, have much thicker myelin sheaths and consequently much higher conductive velocity than whales and elephants. In combination with much shorter distances between cortical neurons, this results in a much higher information processing capacity as a very fundamental basis, not specific basis, for intelligence, like in the computer. This is astonishingly the same. But again, this does not explain the superior intelligence in humans. And I'm sorry, I'm a biologist, a philosopher, but I don't like the idea that humans are superior, but they are in intelligence. Although the difference between chimpanzees and corvid birds is not as large as. So there could be one other possibility at the end, language. All studies made in mammals found out that, of course, apes can be trained to use human language, but not verbal language, but they can use a keyboard or sign language and so on. But they stop, as far as we know, for 50 years at the level of very simple grammatical language, which is found, and I proved it in my grandchildren, from 0 to 2.5 years. There they stop, non-grammatical. This is said by all experts. And then there's an explosion in humans, and I tested this in my grandchildren, and I've forgotten what it was in my children. But I tested very recently, and there's an explosion of syntactical grammatical language. And this is, as far as we know, unique to humans. Maybe in songbirds there is something like a grammar, but it's not established. So humans have not only one language center, the Wernicke speech area, which is present in all land vertebrates, let's say. In addition, we have the Broca area, which is responsible for grammar and syntax, among others, and it develops at an age of 2.5 years. Absolutely exactly when little children start developing syntactical language. So this might be the only unique property of human beings in the brain with respect to all other brains. The only. Not consciousness, not prefrontal cortex, nothing. Maybe a number of neurons, but the only anatomical difference is the anterior part of the Broca speech area. And so, I think the evolution of language about 100,000 years ago, very recent, was a strong boost for human intelligence. There's natural intelligence, which is high in primates, and then we developed syntactical grammatical language, which again boosted our intelligence. The next step was evolution of written language, and the third evolution was this device here. So there are at least 3 boosters, amplifiers for animal intelligence, which explain the difference. Very briefly at the end, I will skip this. What about crows? And they are absolutely intelligent, and it's very astonishing what they can do. But if you look into their brain, you're shocked. This is the seat of intelligence in the avian or in the brain of a corvid bird. It's totally different from the. It appears to be totally different from the cortex of mammals. But friends of mine have shown there are nuclei you cannot see here very nicely, but if you study them carefully, there might be a correlation, anatomic correlation, but what you see here, the neurons are extremely densely packed and very, very small, very small. And if you compare this wiring diagram in mammals, there are 80% pyramidal cells and 20% interneurons, and there are inhibitory and excitatory connections. If you look into the avian brain, you see the same, despite of striking differences in the seat of the cortex. We have 80% excitatory light spiny cells, pyramidal cells, and 20% small cells, excitatory, inhibitory. If you go into details, absolutely the same arrangement, organization. And birds have very tiny brains, but they have tiny neurons, extremely densely packed and high processing velocity. This might explain, and you come up to 500 million, might explain why birds with very small brains are so intelligent, at least at the base. It might be that they have even invented a songbirds language. Thank you for your attention.
Thank you very much, Gerhard. That was very fascinating. We've got time for a couple of questions. I should have pointed out earlier, actually, please use the microphones in front of you. Just push the button and speak, and then when you've stopped speaking, release the button. Okay. Any questions? Yes, Hasselhoff. Use the microphone. It's actually synced with the filming, so it won't go onto the film if you don't use the microphone. Press the button and keep it down.
As an example, how to test intelligence, you had this maze, but you cannot do that with all animals. So how do you grade intelligence between animals with quite different lifestyles, like insects and whales and so on?
Can you repeat it? What was the question?
I think the question was, how do you rate intelligence in animals that have very different lifestyles?
Yeah, this is a big problem. First, you could observe them in nature and test if they do something unexpectedly, novel tools or novel behavior which deviates from expected behavior. This is one approach, but it's rather unreliable, but very important. The other thing, you put them into the laboratory, and you have a set of experiments or tests for intelligence, you just test them. An ape versus a rhesus monkey, which can be done, a dog versus a cat, elephant versus a dolphin. It's difficult, but it's possible, and then you could say, oh, this animal can recognize him or herself in the mirror, but the others don't. A rat cannot. And so this managed to go through the maze, but the other cannot. And so you just make it for 40 years and find you get some kind of a rank. Even it could be done, as my friend Uno Günterkün did it, and many others did it, rank birds and mammals and say, oh, corvid birds are roughly as intelligent as a capuchin monkey or so. So this is somehow fiddling, but there is somehow a ranking order. And this is very flexible, but more or less we could say man is, unfortunately, is on top. And if chimpanzees or gorillas and orangutans, there is no difference, but what about corvid birds? But rhesus monkeys and capuchin monkeys are very smart, but my wife and I studied mammals, and there's a huge difference, and many mammals are really stupid. And you test them very easily, but it stops at mammals. Fish is very different, and so on. So you get some ranking, and it nicely fits to our approach, the number of neurons, and in addition, information processing capacity and learning capacity and communication capacity. This, in addition, could roughly explain why we are so intelligent and other primates are so intelligent.